Hello and welcome to today's webinar presented by Dlubal Software. Today we will be working in our finite element analysis and design software, RFEM. The title for today's webinar is AWC, NDS, Timber Member, and Connection Design in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office located in Philadelphia, Pennsylvania. I'm also a technical support and sales engineer. My colleague Bastian Kuhn will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way of the presentation when you logged into this GoToMeeting, feel free to show or hide that with that orange arrow up at the top. We always want to encourage everyone to ask questions during the presentation as well. You can do so within this same dialog box. We'll do our best to get to all the questions, but if by chance we don't, I'll certainly send you a follow-up email afterwards. So as far as the webinar content for today, we will first go through the generation and loading of a simple timber truss in RFEM. Then we'll take a look at member analysis per the NDS 2015 in our add-on module RF-TIMBER AWC. Next, we'll move on to a different add-on module, RF joints, and as of a couple weeks ago, we added the NDS code for the design of timber connections. Then I want to show you the interaction of internal forces and connection stiffnesses between RF joints and RFEM. And lastly, we will take a look at curved and tapered glue lam design in the add-on module RF-TIMBER AWC. So to explain RFEM and the timber add-on module concept, for those of you who are not familiar with our software, the main program is RFEM. This is where we can integrate with BIM software such as Tekla, Revit, AutoCAD. We'll be doing a majority of our modeling in RFEM. You'll also be loading the structure and creating your load combinations, whether that's manual load combinations or according to our load combination generator per the ASCE 7 or the NBCC code. And lastly, we'll run a full analysis in RFEM. So things like internal forces, deflections, stresses, this can all be done in RFEM alone. But the minute that you would like a check per a specific standard, this is where our add-on modules come into play. For today, we'll be working in RF-TIMBER AWC. This will provide us with member design per the NDS code for both ASD and LRFD. We can also optimize our member based on a specific ratio check. For example, design might be something like 0.8, possibly 0.9. And we can also do a serviceability check, so find out what the limiting deflection ratios are, put those into the add-on module, and see if we're also passing for deflection control. The other add-on module, RF joints, as I mentioned, a new feature was added for the NDS code, both again ASD and LRFD for connection design. It's utilizing steel plates and dowels. And again, I'll show you the interaction that the add-on module can have with RFEM in regards to the actual stiffness properties of a connection and how that affects our internal forces. So with that said, we can jump directly into the RFEM model. So for the sake of time, I did go ahead and create this general truss here, and I am in a 2D environment. So in order to create this truss, I used our structure generator. If we go up to Tools, Generate Model, under Members, you'll notice that we have several options here. A few of them are grayed out, and that's simply because I'm in a 2D environment. But for this example today, I use the 2D truss option. This dialog pops up. You can see all of the different truss types that we have. We have the option to set our diagonals, different directions, and the rest is pretty self-explanatory. We simply give it the number of bays, the total length. It's a pretty large truss for today, so we set this at 85 feet and the total height at 15 feet. Then the program asks us to determine the cross sections, to set those cross sections. So for the upper chord and lower chord, I just gave it general glue lam timber members, as well as those specific properties for a glue lam. I can press my little info button here to see the cross-sectional properties, 6x12 for my upper chord, and for my lower chord, I modeled a 6x10. For the diagonals and verticals, these are just more of post members, 5 inch by 5 inch Douglas fir larch, so a softwood here. Again, the member properties can be viewed. Now, the program automatically sets the member type to beam for the upper and lower chords, and you'll notice that the diagonals are set to truss. For any type of modeling software finite element, we typically have different member types. For our program, beam type is anything that would be a beam or column. Now a truss would be the same thing as a beam, but we've automatically applied the moment end releases to those members. So a truss makes perfect sense for all of our internal members within this truss, that we don't want to transfer any moment to our upper and lower chords. So leaving these settings as is for the member type, we press OK, then we'll get the generation of our timber structure here. Then I did add a pin support on my left-hand side and a simple roller support on my right-hand side. Now, the other thing that we need to take care of is that right now, or actually when I did generate the truss, that a fully rigid connection was available at the top of the truss, also on the left and the right. So you'll notice that I've applied a simple pinned member end release for the top of my truss, just one of the members. You can do so by editing the member, double-clicking it. You'll notice that we have member hinge at the start and member hinge at the end. I just created a moment release, which you can see here in the two-dimensional direction about the local y-axis. Now, I did so at the beginning of the member on my left-hand side and the end of my member on my right-hand side. So modeling is essentially complete for this simple timber truss. I did also apply some loads, and I have two load cases. You'll notice in my drop-down box I have dead load and snow load. So my dead load, if I display it, is just a simple member load, 0.08 kips per foot. The snow load, on the other hand, is 0.12 kips per foot in the projected Z direction. So we're taking into account this member angle and how that load directly applies to these upper chords. Now, I also created a couple of load combinations just manually, and maybe if we enter in the load combinations dialog box, we can see this. So we do have the options to automatically create these load combinations, like I mentioned, per ASCE 7, for example. But for the simplicity of today's example, I created two load combinations. The first could be considered an ASD load combination, where my load factors are 1.0 for dead load and snow load. My second load combination is maybe an LRFD load combination, where I have applied the load factors of 1.4 and 1.6. You can see in this drop-down box we have quick access to them, or we can overwrite them with whatever load factor we would like. So now you have the ability to toggle between the load cases and load combinations, and we can run our first analysis. I can go to calculate, calculate all, and we'll see within a split second the model will be solved. So we are still in RFEM. We haven't touched any of the add-on modules yet. So once we run this analysis, in our project navigator over here, we have the results tab available. And we can, for example, view everything graphically, such as global deformations. We can change the display factors here. What may be a little bit more interesting is to take a look at our member internal forces. Here you can see we have our axial forces. We have some pretty high tension forces on the bottom. We have high compression forces at the top, denoted by the negative magnitude sign here. Taking a look at shear forces, I can always increase my member diagrams here. And lastly, we have our moments. We should have no moment transfer, where I put in those moment hinges as well as along our diagonals and verticals here. Same thing for support reactions. These are controlled here graphically within our results in the project navigator dialog box. And you have full control over colors, sizes of fonts, just by going to Options, Display Properties. Now, this is great graphically, but sometimes we want to see a little bit more information as it relates to the member. So we can always right-click on a specific member and choose Results Diagram. Now you'll see the entire member here. We can turn on more graphs such as internal forces, deflections, and get a more realistic view of what's going on along the length of the member. You can print this off directly to our printout report. You can export directly to Excel for further sorting. So a lot of powerful capabilities in just viewing our analysis only. So now that we have run a full analysis, that's great, but typically as design engineers, we want to move on to code checks. So this is where we are going to make the clear distinction that we're going to utilize an add-on module. In the data navigator over here, you will see the long list of add-on modules. We do work in the add-on module system because we really want to cater the software to your needs. Not everybody is going to be in the Chinese steel design, for example, so why should you pay for it? So we, again, are trying to cater towards your specific design needs. We also have them organized a little bit better with this add-on modules drop down at the top here according to the different materials and applications, dynamic analysis, things like that. So for today, we will launch the RF-TIMBER AWC. Now, to begin with, you'll notice we have both ASD and LRFD, so that's nice. Some other software programs for timber design only give you ASD, for example, so you have complete control over which design method you would like to run. Today, we will choose the LRFD. Now, the ultimate limit state design, you'll notice that my load combinations and cases were brought in from RFEM, so I don't need to redefine any of that. So ultimate limit state, we'll choose our LRFD load combination, and serviceability, we will choose our ASD load combination. Now, the next thing to go ahead and define are which members or sets of members would we like to design. So let me quickly explain that when we go back to this add-on module, if I zoom in here, the program automatically created a set of members with the truss generation for my bottom chord, and I also have a set of members for my upper chord. What I wanted to mention is if you do zoom in, you can see a faint dotted line around it. I know that's hard for you guys to see, but if you were in the software, you'd be able to hover over that and see it's a set of members. A set of members will essentially be designed like a continuous beam. You know, we don't want to optimize one of these individual members different from its adjacent members. We want to get a code check for this entire bottom chord. So that's where the sets of members comes into play. Now the default is to select all members. I'm going to clear this, and for my member design, I'll scroll in here and I can just use my selection dialog box, my selection box, similar to what you would find in AutoCAD, for example, to select all of my internal diagonals and verticals for my member design. And for my sets of members, I simply choose graphically the upper chord and the lower chord, and we click OK. So now we have the distinction between members and sets of members for what we'll be doing for design purposes. Now all I need to do is to simply move down the list. Next we will go to materials. Again, everything is brought in from RFEM, so I don't have to redefine my materials, my geometry, my cross sections. All that we're doing in this add-on module is giving some further design information related directly to the NDS code. Now you'll notice that we have two bright red materials here, and that's just because when I open up a new model, concrete and steel are defaults within the program. I can delete these back in RFEM if I wanted to, but all the program is telling me is that these are not applicable in the timber add-on module. That makes sense. But our two materials that we did define to our members back in RFEM are applicable. I can click them and view all of the material properties that will go into the design of this member. Again, cross-sections, same concept. The member cross-sections are brought in from RFEM. I can view some of the cross-sectional properties here again if I'm interested in them. And we can move on to load duration. Now, this is load duration factors. We assign dead load and snow load to the applicable loads that I applied in RFEM. The program is smart enough to know what load duration factors to apply to this. Now, we can always use our drop-down box to adjust these, but even more so, there is the standards button down at the bottom of the dialog box. So the standards button will show you every single factor that is going into the design process within this add-on module. So for example, the load duration factors. What is nice is that you can adjust these if for some reason you don't fall between 10 years and 2 months, but somewhere in between, you can adjust them. That's completely up to you. Then you'll notice some of the other factors such as temperature factor, wet service factor. If we go to the others tab, repetitive member, shear reduction factors. Again, this is just all the information from the code. Under the use standards, we just list for you to know which standards are being utilized for the design, which you'll see at the end, we give you references to these standards as well. So moving on down the list to in-service conditions. Again, this just comes from our standards button down here, moisture service conditions. Are the members dry or are they wet? Our temperature ranges, we can change these if we would like. Now you'll notice that we have two separate tables for members versus sets of members. This is just so we don't group everything together. I think it's laid out a little bit nicer when we separate members versus sets of members, and then we can control those factors individually. Effective lengths for members. So this is stability checks. You'll notice that we have buckling about the weak axis, buckling about the strong axis, and lateral torsional buckling. So I'm going to assume for all of my internal diagonals and verticals here that buckling about the strong and weak axis as well as lateral torsional buckling is a concern. So I'm just going to leave everything as is here, that I'm going to let the program determine if this is okay based on my design. Now the effective lengths here default to the full member length, but you can easily control these lengths by typing it in or graphically using the measuring tool here, so you have complete control over this. Now again, our sets of members is on a separate table. And for my upper and lower chord, I'm going to assume that I have complete lateral bracing along the length of the member. So therefore, weak axis buckling about the local x-axis, which I have my axes shown down here, is not a concern to me. And it would be the same thing for my lateral torsional buckling. So this is not a concern based on my connections or my lateral bracings. All I have to do is just to simply uncheck the possible. Buckling about the y-axis or the strong axis, I am still concerned with this, but right now it is set to the full member length, the full set of member length. So it's pretty large, 90 feet and 85 feet. Maybe for uplift wind purposes, I have much smaller unbraced lengths here. For example, the upper might be 3 feet and then the lower might be 3.5 feet. So as a design engineer, you always want to pay careful attention to your unbraced lengths because this significantly affects our stability design. Okay, so moving on to additional design parameters here. This is just shear reduction factors, edge bonded. This refers to our glulam members for our upper and lower chord members. We have the code references here. Again, the standards button will tell you what those factors are. If we scroll down a little bit further, here's our incising factors and repetitive factors for our post or our brace members within the truss. And we can move on down to the serviceability data. Here is just deflection checks. We can check every single member if we'd like to in our model, or maybe we're only concerned with checking a couple of members. So for this example, I will graphically choose perhaps maybe one of my diagonals here that I want to check my deflections. I click OK. The manual reference length is set to the full length of the member. That's fine. Do I have a pre-camber? If so, I could put this in here. And lastly, I need to specify if this is a beam or cantilever. Now I can do the same thing with a set of members. So maybe I'm interested in my bottom chord deflection. Well, all I need to do is to graphically select my bottom chord here. The full reference length is set at 85 feet. And again, we just use the beam type beam. Now the question is, what deflection ratios am I comparing this to? Where can I control that? Well, under the Details tab under Serviceability, here's my limiting deflection ratio. You can see the default is set at L/360. Now for cantilevers, it will always use 1/2 of this ratio that you set in here. Then you need to specify whether the deformation is relative to the shifted member ends or the undeformed system. This may be better known as relative versus absolute deformation. So this is where we can control this limiting deflection ratio and change that if we'd like to. And lastly, we can move on to the cross-sectional area reduction. This is if we have a notch within our member. Maybe the member connection at the ends, or maybe the member is sitting on top of a wall or another member, and we have to take this cross-sectional notch out of the member. We can easily account for this by just selecting the member graphically again, and then giving where the notch location is, whether that's the start, the end, or within the inner span here. Then we just give the notch the geometry, and the program will automatically account for that cross-sectional area reduction. So it's smart enough to only compare those internal forces at this notch location for design purposes, meaning we don't have to reduce the entire cross-section of our member and get an over-conservative design. So just a nice little additional feature if you do have this scenario. For our case, we won't do that today. Now, before running the calculation, I want to quickly run through the rest of the details tabs. What is exactly going on behind the scenes here with some of these other options? So the first one under resistance is consideration of connections, the reduction of limit tension stresses. So if I check this, what this means is that occasionally we have the weakening of a cross-section at a connection. So what I can do is check this checkbox, and all I need to do is to select a node, and here I give the connection length. Maybe that's 6 inches, maybe that's 1 foot, and I can actually reduce the stress ratio inside that connection. You can see the default is set to 60% here. And the stress ratio outside the connection can be kept to 100%. So now when we're looking at our design, the program will flag you if at that particular node you're exceeding that 60% stress ratio. So just an easy way to take into account the weakening at a particular connection of your cross sections. Positive or negative bending about the positive Z, positive Y axis. What this is used for is for glulam beams. They sometimes have, or not sometimes, they always have different bending design values for our top versus our bottom in tension and whether our moment is positive or negative. So default in the program, the positive local axis for Z is pointing down for our members. So typically you won't be adjusting this unless you're rearranging the local axes of your members. So that's just what that is in reference to for our glulam beams. Now, limit value for special cases. This refers to torsion. The NDS code does not give us much in terms of torsion design. So for you as the engineer, you can decide if torsion is of no concern to you. You can change this to ignore torsion here. The other option is to allow further design if the shear stresses due to torsion do not exceed this limit ratio that we set in here. So you'll notice that we have the shear stresses due to torsion over our shear resistance capacity values here. Now this ratio, 0.05, is default within the program. This does not come from the standard, so it's up to you as the user to adjust this ratio if torsion is a concern for you, and we will certainly take it into account for design purposes. Under the Stability tab, we have Perform Stability Analysis is automatically checked. If I were to turn this off, click OK, you'll notice the effective lengths where I put in for strong and weak axis buckling, those are gone now. So I'm telling the program I have no concern with buckling or lateral torsional buckling, so completely ignore this for my design. Now, again, the default is to have this turned on. We've already been through this with our particular tables. And what we're doing is we're doing a stability analysis according to the equivalent member method. So with the equivalent member method, the NDS says to take into account secondary effects within the design phase for our structure. Now this is very different than something like steel, for example. Steel tells us to take into account secondary effects in the analysis section. So things like P delta, stiffness reductions, notional loads are all taken into account in RFEM, the analysis side. But again, timber's a little bit different in that we have these factors added to our bending capacities, for example. So with that said, it is okay back in RFEM, if I open up my load combinations, you'll notice that under calculation parameters, it is always default in the program to run a second order analysis for our load combinations. This will take into account P big delta and P little delta. So perhaps you have an existing structure, or you're just really close on your design checks and you don't want to increase your member sizes. Technically, you can go back into RFEM, change this to a geometrically linear analysis, and then you can take into account the second order effects within the add-on module only, so the design part of it. Now, it is typical for most engineers just to leave on P delta analysis in RFEM, therefore your internal forces are a little bit higher, but it's just a more conservative route to take. Now, the other option within here is stress stability analysis according to second order theory. It requires definition of imperfections in RFEM. If I were to check this, what I'm doing is I'm telling the program under the effective lengths that the buckling for strong and weak axis, I'll take that into account with the analysis. Maybe that's with stiffness reductions or with those notional loads, imperfections, things like that. With lateral torsional buckling, there is no way to take that into account with the analysis side, so I'd like to still do a check with that within the design side. Regardless, today we will stick with the default of checking, again, our strong and weak axis buckling. Serviceability, we've already been through, and on the other tab, cross-section optimization. So design ratios are maybe more around 0.8, possibly 0.9. It's typically not 1.0. So for optimization for your members, which I'll show you in just a second, you can change this to 0.8, for example, for design purposes. Check of member slenderness. If member slenderness is a concern, here are the ratios that we have set according to the code for flexure members, compression members. You will need to activate 3.3 member slenderness right here for our result windows if you are wanting to check for member slenderness. So that's pretty much the concept for all of the input data, and now we're ready to run our first calculation. You can see that solves within a quick second. All it's doing, bringing the internal forces into this add-on module from RFEM, and we apply the NDS code for our design. Now we have our results tables available, and we can view the design by load case. We can view design by cross-section. We have 3 different cross-sections here. Maybe we want to view design by the sets of members or by each individual member. Now, what's also great is that as I'm clicking through these tables, you'll notice that it is synced to the graphics view in RFEM. Even the X location of my controlling internal forces line up with my tables here. And something else that I really pride ourselves on, because I know this isn't available in a lot of other software, is that we give you the code check for everything within the NDS. So we're not just giving you the controlling code check for each member, but you can actually scroll through and view the different checks individually. Even more so, we give you all of the variables that go into that code check, as well as the equation references. So if you have the NDS code right in front of you, here's the equation for your C sub P factor. You can quickly flip to it and understand where those numbers are coming from. So again, a very powerful feature. Now you can always export directly to Excel to do some further sorting, and as you can see, we have this nice big green smiley face because our design check is only at 0.5. So looks like we're doing quite well with our design. We can also view some of the governing internal forces by member if you are interested in that. And lastly, we have a parts list by member or a material takeoff. So as far as optimization, just to quickly touch on that, if we go back to our cross sections table here, you'll notice that the max design ratio for each cross-section is given. I think we can see that our top chord is pretty low, 0.22. So maybe this isn't an ideal cross-section to have, and rather we'd like to optimize to something more like 0.8. Well, again, we control that 0.8 under our details setting, and here is where we can choose the option to optimize. When I click yes, then all I need to do is give the program some dimension ranges for both my depth and my height, like maybe 4 inches to 20 inches with an increment of 0.5 inches. So then the program, we can just rerun the calculation, the program will optimize, and we can continue on with using these new section sizes. For connection purposes, I'm not going to do this, so we'll just stick with the design that we're given. Lastly, we can view everything graphically. We're back in RFEM, but we're still technically in the add-on module, which you can see from the drop-down box and this little dialog box here. We're still in RF-TIMBER AWC. So I can view my ultimate limit state designs, which you can see graphically here, and I can turn on my panel. Well below 1.0, we can print these off. Serviceability we can take a look at. Remember, we only check serviceability deflections for our set of members down at the bottom and one single member here. So graphically, we can view everything rather than just the tables. So that basically sums up the member design. And the next thing that we want to move on to is connection design. So I can go back to my data tab, and I have my other add-on module here, RF joints, and I will launch that. So again, just another simple dialog box, which is the add-on module, taking in all the internal forces into this add-on module. We just need to further specify some information. You'll notice that we do have steel and timber. Unfortunately, at the moment, steel is only per Eurocode design, but at some point in the future, we do plan to add AISC as well as CSA steel connections. But what is exciting is that we did add the NDS 2015 for our timber connections. You can see we have both ASD and LRFD available. Maybe to just continue on from our member design, we will stick with LRFD design. We have steel to timber connections. Now the joint categories, we either have general dowels we can choose from, or you can also see that we have bolts. For today, we will be going with general dowels. Now, 3 different joint types. We have the first joint type, which is main member only. Maybe you have the cantilever of a beam from a wall, for example. Well, that would be applicable for this type of connection. The second connection type would be with a continuous member and a second member framing in. Well, that might be something more like this connection here, where we have our continuous upper cord and we have a vertical framing into that continuous member. And lastly, we have without continuous member. So at this particular connection joint, we don't have any continuous members that we're wanting to define. So this is what we'll be continuing on with today. As far as the cutting of the main member and connected members, I'm going to pause on this, and we'll get back to this because it'll make more sense once we're visually looking at our connection. Steel plate material, from this drop-down box, you can see we have several ASTM materials to choose from, but if by chance you don't see what you would like, you can always enter in your own user-defined steel materials with yield strength, ultimate, and Euler buckling strengths here. For today, we'll stick with the A36 material. The fastener material, again, some ASTM standards or user-defined. We will stick with J429 with a yield KSI of 48. The checkbox calculate with members in contact. If we were to turn this on, this essentially just tells us, okay, that we're considering 2 members are in contact. And if we have extremely high pressures from one member down onto the other member, some high pressures, the program will actually flag us and tell us, well, this is something that you may want to look into further. So we don't give you design for these members in contact, but it's just an additional check to notify you if we do have some extremely high pressures from one member to another. So again, we just simply work down our list here. We'll move on to nodes and members. Now our little graphics view, you will see our truss. This is brought in from RFEM, and nothing's highlighted right now. Everything's grayed out because we haven't selected any nodes in particular. Now this is import from the structural model, or we can set manually here. Now if we choose set manually, what this allows us to do is to really define any type of connection that we want, including the materials, the cross sections. We can define different angles, so we don't have to use what we had modeled here in RFEM. For today, it definitely makes more sense to import in what we've already modeled in RFEM, so we can do a further connection design here. The first thing I want to do is to choose my nodes that I'd like to consider for my first connection. Well, I'm going to choose node number 1 on my left and node number 2 on my right. These will be identical connection designs, so we'll use those. Should the geometry of the connections be set to the default geometry? Yes, I want to bring in what RFEM already has modeled. Now you can see I can zoom in here and my members are highlighted at that particular connection. So at node number 1, the program automatically assigned the connected member to member number 1. And if I use my drop down, I have connected member, main member, inactive. Now member number 9 at the bottom is set to the main member. My materials and cross sections were automatically brought in from RFEM. Even my angles were automatically determined, so I don't have to worry about redefining that information. Quickly jumping to geometry. Now our picture of our connection will be populated here, and I think we're all in agreement that this is not the ideal connection. Nobody would cut these two members right down the middle and create a connection by any means looking like this. So how do we change this? Well, back on the General Data tab, this is where the cutting of the main member and connected members are affected. So I'm going to change this to the second option, which you can see here graphically. Now jumping back to my to my geometry tab, well, this is looking a little bit better. But ideally, all of these internal forces from our upper chord are going to be bearing down on our bottom chord. Timber is not very strong when we're considering these internal forces bearing down here. So I want to flip-flop these, so to speak. I can do so under the nodes and members, and instead of member number 1 being the connected member, all I'm going to do is use my drop-down box to change that to the main member. Now, member number 9, I'm going to set this as the connected member. The program tells me the first node changed. Do you want the other nodes to be changed? I'm going to say yes. It's going to bring in the geometry from RFEM. So now automatically node number 2 is changed as well. So jumping back to the geometry tab, this looks much better. We have those internal forces directed to the support, which is exactly what we want, and then our lower chord is simply framing into that upper chord. So now that we have defined our geometry under nodes and members, we can move on to loads. What is the load combination that we'd like to use for design? Well, since we're doing LRFD design, I'll choose my LRFD load combination. Load duration and service conditions, this should look pretty familiar to what we just saw in our AWC module, our member design module. Things like load duration factors, moisture conditions, moisture service conditions, temperature. Again, if we pop open this standard, well, here is where we can see all of the different factors that are applied for the connection design. We can scroll through these. Everything's just coming directly from the NDS code. So lastly, moving on to geometry. So this is probably the most important because here is where we are going to define our dowel layout and our steel plate layout. It's pretty self-explanatory. All I need to do, again, is work from top to bottom, filling out each variable here. Now, the shape of the steel plate, the first option is user-defined, which you can see that this is basic, just rectangular sections at my upper chord and my lower chord. The second option is convex hole. What the program will do the best attempt it can to simply connect these two rectangles with a straight line. So maybe this is something a little bit more similar to what we'd see actually fabricated. So that's an option if you'd like. And the third option is rectangle. You can see this is not ideal for our connection today, but this could be ideal for another scenario. We'll just stick with this user-defined connection for now. Now, the number of steel plates can vary anywhere between 1 and 5 steel plates. For the first run, we'll stick with 1 steel plate. We do need to give the thickness of the plate. We'll set that to 0.5 inches. Now the distance from the dowels to the plate edge, E1, we do our best to give you all of these variables graphically as well, so you can kind of understand exactly what information you're entering in here. So for that edge distance, we will set that at 1.2. Now, is the width of the slot the same as the thickness of the plate? Well, if this was not, then I could specify the slot thickness different from the thickness of the plate if I would like to. Moving on to the connection geometry, you can see that we have the main member here, or we have connected members. So we first want to start with our main member. The pattern will always be rectangular. The fastener diameter, which we can change our viewport here and zoom in to see exactly what we're setting in terms of our dowel layout. we will set our fastener diameter to 0.5 inches. Now the dowel length is automatically calculated simply based on the thickness of my member, my glue lamb member. So this is set at 6 inches for the thickness of the member. Now perhaps I would like to maybe not see the dowel holes, for example, and I want to put a plug on either side of these. Well, here's where you can set that plug length of maybe 0.5 inches. And you'll notice that the dowel length is automatically takes that into consideration and reduces to 5 inches. For today, we will leave the plug length as 0. Now the number of dowel columns, we can set this to 8. The number of dowel rows, we will set this to 4. The little picture automatically updates here. Staggered rows. This is just a more economical design. We still have 8 columns and 4 rows, but because our bolts are staggered, we can get away with a few less dowels or bolts. The method of dowel group placement, we have 3 options here: the minimum edge distance, the minimum dowel spacing, or user defined. So the first 2 here are just according to the NDS code. So for this first run, we'll just stick with the minimum edge distance. Now the geometry factor comes from NDS code table 13.3. We can adjust this if we see that fit. The orientation of rows and columns, the default is set to basic. You can change this to rotated, where the program will automatically rotate that 90 degrees. Maybe we want it slanting, which is an interesting configuration where it will fit them all at the bottom of the member here. Or the fourth option is user defined, where we can define an angle and a rotation here. We'll just stick with the basic layout for this example. Shear reduction factors, shear edge bonded factors, again relate to our glue lamb members. So we have this set for our main member. Now we'd like to use our drop-down box to move on to the connected member. So for the connected member, we need to make some changes here again. The fastener diameter, we'll set this at 0.5 inches. The number of dowel columns, we will set this to 10. And the number of dowel rows, we'll set this to 2. I would like to utilize staggered rows if possible, and we'll leave this at the minimum edge distance. So now we're ready to essentially run the analysis for our first connection. All we need to do is run calculation. Again, the program quickly cycles through that, and we come up with our connection design. So what's initially shown here is our main member and our connected member. I think what's probably standing out to us is this bright red number of 4.61. That's certainly not okay. If we're looking at a few of these other checks, again, complete code transparency, so to speak, for our connection. We give you the code check for everything. If we're cycling down through these, and we will get to dowel group, load carrying capacity of a single dowel. Well, we're extremely overstressed for this. Maybe I want to scroll down through, see where some of my numbers are coming from. All of the factors are listed. Here are all of my equations directly from the NDS code. And lastly, my extremely high ratio of 4.61. Scrolling down to my connected member, I obviously have a huge problem here as well. My load carrying capacity of a single dowel is exceeded. So before checking out the rest of the results, let's go back to our geometry and make some changes here. Maybe the first change I'd like to make is I'm going to add an extra steel plate. It's asking me, do I want to delete my results? Yes, this is fine. Now I can kind of rotate this view around, and you can see that these steel plates are shown here graphically quite nice. It's a nice rendered view where we can actually see what's going on. Now, there are a few other settings that came up with adding 2 steel plates. For example, we can set these as side plates if we wanted. So rather than be embedded within the glue lamb members, you can see now they are side plates. For us, we will uncheck this option, and the third option is the uniform placement over plates over the width, which you can see from this cross section here. If I uncheck this, then I can set my distance between the plates, T2 here in the center. Maybe I want something more like 2 inches. So you have control over that. It doesn't necessarily need to be the same width for all 3 dimensions. Looking at our connected member number 1, well, I'm going to leave most of this as is except for the method of dowel group placement. So sorry, I want to switch this over to the main member first of all. So we'll scroll in here to our main member. Now instead of the minimum edge distance, I'm going to choose a user-defined setting here. So the distance between dowel columns, which you can see everything is shown graphically here, again, for what numbers I'm entering for my variables. Perhaps the distance between the dowel columns, we'll set this at 5 inches. The distance between the rows, we can change this to 2.5 inches. And the distance from the loaded end to the dowel, A3, which you can see here, we will set this to 6 inches. Eccentricity, if you want to move this connection up or down, you can do so as well with the generation of this eccentricity setting. Now everything else will leave the same for this main member. Connected member number 1, remember we're extremely overstressed here. There were pretty high tension forces on this lower cord. So maybe I want to space out these dowels a little bit more to get a little bit more capacity down here at the bottom. Now we did add a second steel plate, so that will help us as well. So instead of the minimum edge distance, I'm going to use these user-defined settings as well. So my distance A1 between my dowel columns, I'll set this now to 5.0. And the distance between rows will be 6.0, and the distance to the edge, A3, will now be 6.0 as well. No eccentricities. So now that I've made these slight adjustments, we can quickly rerun the calculation with this new geometry to take a look at our results. It looks like we're still slightly overstressed, 1.23. Well, at least we're doing a lot better than the 4 point whatever it was code check from before. So we're almost there. If I scroll down to my connected member, I'm now at 0.8 is my controlling code check here for my load carrying capacity. That's great for design purposes. So I think we're done with that connected member. But we still want to go back and address the main member quickly. Well, maybe I don't want to add any additional dowel rows or columns. I'm content with the size of my dowels. So what I can do is just to simply uncheck my staggered. Do I want to delete my results? Yes, that's fine. So now instead of staggered rows, you'll see that I have a true 8 columns and 4 rows. And so we have a few additional dowels added to this connection. We'll run the calculation again. And I think that we'll see now our controlling code check is 0.82. So that is good for design purposes. So now taking a look at some of the other design tables that we have, designed by load case here. We only have one load combination we're solving for, designed by the 2 nodes, node 1 or node 2. Maybe the most user-friendly table would be this design details. Here you can see that the ratio checks are set in descending order from the most controlling to the least controlling, but we also have the checks for minimum edge distances and dowel spacings. And again, everything is transparent as possible with the code equations and references. Even the internal forces that we're designing for at that particular location are listed. Our geometry here is just the geometry of the plates. You know, most of this was in user input, but things like the slip modulus for when fasteners, given the slip modulus for the connections, things like that. Now, our last graphic here is pretty powerful as well. Obviously, we're not a program that's going to give you shop drawings or fabrication drawings for these steel plates, but what we can do is provide you a quick link to create a DXF file for this connection. So you might want to be doing additional drawings in AutoCAD, for example. Well, at the click of a button, you can create that DXF file if you would like to. So again, a pretty powerful feature here for our connection layout. So that sums up the first connection design, and real quickly we can go to graphics, and the program will automatically bring that connection back into RFEM for the graphic view. We can even rotate our member around and see the dowels and the steel plates in there. So in terms of actual rendering, everything is shown there. Going back to the add-on module, I'm going to do a second connection design pretty quick. So we'll just create a new case here. You can rename it if you'd like. And again, just jumping through some of this user input entry that we've already been through, we'll create without a continuous member. We are doing LRFD design, and everything else we can keep as is. The nodes and members for this connection, I'm going to choose the top of my truss. And I click OK. Should the geometry be brought in from RFEM? Yes. Now you can see that we have 4 members for this connection design. The program automatically assigned the connected members and the main member to the individual members that it brought in from RFEM. So how do we think this connection will look with how the program assigned it will look? For this, we jump back to our geometry tab and we take a look at our connection, and I think we can all agree that this is a pretty big mess. This is certainly not what would be ever created by the contractor, for example. So we can adjust this back under our nodes and members, and the main member right now is set to this brace. Instead, I'm going to set the main member to my upper chord. Now my brace, I'm going to change this to connected member, and the program has automatically rearranged all of this, so we'll jump back to our geometry, and this connection looks much better. Now, one quick note about this, when you have multiple members, you'll notice that we now have priorities. So it looks like the program automatically assigned the correct priorities for now, but let's say the other upper chord here, it is assigned to priority number 3. Well, again, jumping back to my geometry tab, we have a mess again. So if you're not seeing what you like, you can just make some further adjustments rather than what the program automatically set these members to, whether that's in the nodes and members or under the cutting of the main member and connected members. So eventually you'll get the connection that you would like. It just may require some adjustments here. So for now, we'll change this back to priority 1, and we should be good to go. As far as loads, we're choosing our LRFD load combination, the load duration and service conditions. We're not changing anything here. We'll leave this all to default. So real quickly, since we've been through most of this, we will just fly through some of the user input for our connection data. I'm going to automatically assume we're going to need 2 steel plates here. The thickness of the steel plate will be 0.5 inches. The distance from the dowels to the plate edge will be 1.2. This dimension here in the middle, I'm going to again set this to 2 inches. So this coincides with my connection at the bottom of the truss too. So my main member here is the first member I'd like to create. The fastener diameter, 0.5 inches. The number of dowel columns, I'm going to set this as 8 columns, and we will set this as 3 rows. I will utilize a staggered effect here, which we can change around our dimensions to view this a little bit better. And I'm just going to go with the minimum edge distance. So now that I've defined this main member on my left, my upper chord, I probably want to do some same setups for my upper chord on the right. So how do I quickly do this? Well, this is where we allow you to actually save the fastener group to the library. So here is where I can give it a name such as main 1, for example. I click OK. Now I use my drop down to drop to connected member number 1. All I have to do is to open up my fastener library here. I can click on main 1, I click OK, and everything is updated automatically according to what I just saved. Now what's nice about this is this fastener library isn't just for this model that we're in right now, but you can save fastener connection layouts between different RFEM models. So a little bit more efficient than manually going in and having to redefine this, especially if you're doing a lot of structures that have similar layouts. So that's a nice feature. Now dropping down quickly to the connected member, you can see this is a pretty slim member here. So we want to define our settings accordingly to 0.5 for the fastener diameter. The number of dowel columns, for this one we will set this equal to 6, but I only want 1 row. Now the staggered effect you can see really doesn't matter whether I have this checked on or off. The minimum edge distance, we'll leave this the same. You will see that now we have the option for member eccentricity in the X and Z direction. So if I physically want to move this brace member to the left, to the right, up, down, I can change that here by just simply adding in that distance. Now keep this in mind because I'll show you in a minute how to export these eccentricities back into RFEM. For today, I'm not going to put any eccentricities in there, but just know that that's an option if you don't quite see the layout that you would like. What's also impressive is that the program automatically knows that this is not a glulam member simply based on the material settings alone. So now we have things like the incising factor, repetitive factor, size factors for this simple post or brace member that are applicable. So again, you don't have to manually apply these factors, but the program knows, well, they automatically have to be assigned according to the NDS code. Again, we'll just leave all of these as default according to our standards button down here. We can save this again. We will call this one brace 1. Now I drop down to my connected member number 3. I open up my library. I select brace 1. I click OK. Everything is automatically updated. So very efficient way to pull up the already membered settings from the other brace. Now we're ready to run a calculation. So again, solves rather quickly. You can see that this brace connection went over a little bit better than last one. We have a controlling code check of 0.52 here. So everything looks great in terms of that. Again, we can view everything graphically for this connection here. Under the drop-down box, you'll notice that we have our first load case for our joint and our second load case. So right now we're in the second load case viewing this connection. Again, I can kind of rotate my settings here to see these steel plates embedded within my glulam members. So that really is connection design, but the last thing I want to show you is the interaction of RF joints with RFEM. So what do I mean by that? Well, under the details, we have the option to, first of all, generate the member eccentricity. So remember with the braces, I told you you could move that in the X or global X or Y direction. Well, with this option checked here, the program can automatically export little rigid links to move that brace back in RFEM, whichever way you specified in RF joints. Now, I'm not utilizing that today, but what I am going to utilize is the generate connection model of a joint or a hinge. Now, before I do this, there are some prerequisites, and if you don't do this, you will get some just simple warnings within the program. So if you do forget this part, the program will remind you. But the first thing that I want to do is I'm going to change this back to RFEM just for the simplicity. So I'm no longer in the add-on module, and I'm going to select all of my members here. I'm going to right-click, I'm going to select member and edit. So remember that right now we have some truss members and we have some beam members. Well, in order to export out my RF joint settings, all of my members need to be beams. That's just for the simplicity of the program. So that's fine. I'm going to set all of these to beams. Now the other thing I'm going to do is I'm going to get rid of all of my member hinges. Remember I applied member hinges up at the top here and up at the sides. So now every single member hinge will be set to none, and I click OK. So we did do connection design at the top here and at the left and the right of the truss, but I did not do connection design, simply for the sake of time, for these other members. So in order to get accurate internal forces, what I do need to do is to hold down my control key and select all of these members that I did not do connection design. I'm going to right-click, edit my member again, and for this one, I will add back in that moment release at the member ends. This is simply because I don't want moment transfer to my upper and lower cords. Now for this one, I did do a connection design at the top, but at the bottom I didn't. So at the member start, I'm going to add back in that moment release, and at the member end for this member, I will add back in that moment release. So now the model is set up accordingly, so we can jump back into RF joints. And under the Details tab, we will generate the member eccentricity with the Generate Connection Model. So I'm going to click OK, click OK, and now we get these funny little looking boxes where my connection designs are. So what is exactly going on here? Well, I'm going to turn this to wireframe so we can see this a little bit better. Now, the first thing the program's doing, if I double click on this box here, is it's done a complete nodal release. So it has released member 9, my lower member, from this support. And instead, it's connecting member 9 with a little fictitious rigid link to my upper cord. Now, the significance of the location of this fictitious rigid link is that this is the center of gravity of my steel plate for my upper cord and the center of gravity for the steel plate at my lower cord. So we're actually taking into account the geometry of that connection. Now, double-clicking on one of these other blue boxes, you'll see Edit Joint. So this is what's being exported from RF joints. Here's a nice picture because it can be a little bit overwhelming. We show you the generated member, the rigid member here, and more importantly, the member end releases for this rigid member is a partial fixity. And if I take a look at the details here, the partial fixity is based on the stiffnesses exported from RF joints. So the different degrees of freedom are actually calculated based on my true connection in RF joints. So now instead of representing my connection by a single node here with my nodal release, well, now I really have the true connection in the model based on the accurate stiffnesses. So pretty powerful feature, and I can take a look up here at the top. I now have all of these fictitious rigid links here connected at the center of gravity for all 4 of my steel plates. I can double click and take a look at this joint. Again, I have 4 different member end partial fixities here based on the stiffnesses from the connections brought in from RF joints. So now back in RFEM, if I were to run a simple load combination here, my LRFD load combination. Oh, one more thing I forgot to mention. Sets of members. So the set of members was automatically created, which I did mention for our truss generator. But now that we have this nodal release up here at the top, the set of members for my upper chord is irrelevant. The program just gave me an error about that. So what I want to do is to redefine my set of members as 2 separate set of members now. So I can right click, create sets of members, 1 continuous member, but I need to create a second set of members here by holding down my control key. So now these can still be designed as 1 continuous member, but because we have this joint release up here at the top from RF joints, we can't create 1 set of member for this entire top chord. So running the analysis again quickly in RFEM, we can take a look at our internal forces. So now you'll notice that the program will actually use these internal forces at the center of gravity at that connection. So that's essentially what we want to represent with these joints is the actual stiffness that's going on as well as the geometry. Same thing for down here. You can see that we have a little moment spike here as well as if we're taking a look at shear because we have a cantilever now from the support to the connection. Ideally, we want to go back into RF joints here. We can go to add-on modules, current module, and we'd rerun our calculation for both connections. That's because our internal forces slightly change now that we're taking into account the true stiffness. It looks like our code check is at 0.88, a little bit higher, but we're still okay in terms of our design. And we'd want to run the design for node number 6 as well. So again, a pretty powerful feature if you want to truly take into account the stiffness and the geometry of that connection back in your model. Now, the last thing I want to show you before wrapping up the webinar is tapered and glulam members. The reason I'm only spending a couple minutes on this is because it really doesn't vary too much from the design that we've already done. So not much time needs to be spent on it. But I do get asked the question quite often, well, how does your program handle tapered and curved glulam members? Well, you can see that our first member here is just a simple tapered member, and how we define a taper is 2 different cross sections at the start and at the end. A pretty deep member we're looking at here, 22 inches in depth for the start, and at the end we have a depth of 49.5 inches. Again, it's assigned as a glulam material, so the program automatically recognizes that. As far as the curved member, these are 4 different beam elements. So again, I created a set of members so I can do design for this entire beam as a whole rather than each individual member. Now, jumping into the RF-TIMBER AWC, I have already created 2 separate cases. The first is tapered glulam, so I'm only doing design of my, let me scroll out here, of my member number 1 for my first case. And then under the second case, curved glulam, I'm doing design of my set number 1. So you'll also notice I'm running LRFD for my curved member here, but my tapered member, I'm running ASD. So you can even run different design methods within the program if you'd like to. So there's two different distinctions with the curved and tapered glue lamps in comparison to our straight, just typical members that we did before. The first is under load duration. You'll notice now that we have a loading condition for radial stress design. Well, if we use a drop-down box here, we have two options, other types of loading or wind or earthquake loading. This simply comes from table 5.28 in the code, and for tapered members, it's important because it's needed for stress interaction factors from 5.3.9. So you can specify that type of loading here. Now, the other thing is that a new table was automatically created because the program recognized that this is a tapered member called 1.10 tapered members. Simply the cross-section at the start, cross-section at the end, the length is automatically brought in as well as the angle of the taper. Now there is one thing that we do need to specify, and that's just the grain parallel to edge. So for this, just quickly jumping back to the PowerPoint, I want to show graphically what this means. Typically a beam, the bottom of a beam will be in tension. That's for most cases, not all. And according to the NDS code 5.3.9, it is never recommended to put the cut face of a glue lamp in tension. Now this would be that bottom picture, and I think we can all see why. I mean, we have these different glued laminates at the bottom. We put them in tension, well, we might have issues. So it's always recommended to put the grain parallel to the edge in the positive local z-axis, which is what you're seeing with this top picture up here. Going back to RFEM, that's the default. Now there are cases such as if a beam is in uplift, for example, or maybe a cantilever, or anything of the sort where you can use your engineering judgment to change this to something otherwise. Now as far as the design, we can jump down to design by member. Really not much is different, of course, other than our code references. If we take a look at some of the code references here, you'll see equations from chapter 5. This is the glue lamp chapter in reference to tapered and curved glue lamps as well, and the program just automatically does those checks for us. Now the other thing to jump to is the curved glue lamp. Again, two differences. Load duration, again we have the radial stress design. This is a little bit more significant for curved members for the radial tension stress capacity. Looking at the curved members table that was automatically calculated, this is a little bit different because for curved members we have the minimum radius of curvature for the inside face. And what this is the ratio check for the thickness of the laminate over the minimum radius of curvature. And from the NDS 5.3.8, it tells us that for hardwoods and southern pine, this ratio must be less than 1/100. For softwoods, such as what we have today with Douglas fir larch, it must be less than 1/125. The program automatically detects what material we're using. It knows the radius curvature simply from the geometry in RFEM. What we do need to define is the thickness of the laminate, which you can see that's set to 1.5 here, so the program will check that ratio for you. Radial stress design is automatically checked as well. You can uncheck this if maybe you have reinforcement at the ends of your curved glue lamp members that radial stresses is not of concern for you. Again, running the calculation here quickly, nothing is different in terms of taking a look at our results tables other than our code references to Chapter 5 to the glue lamp members. So with that said, you can see I just quickly flew through that, but the reason why is really not much changes, and program pretty much automatically detects these types of members and will kind of point you in the right direction for your user input. So with that said, we can wrap up this webinar today. I know that this was quite a lot of information, so we always have more information on the add-on modules you saw today, as well as RFEM at our website, dlubal.com. A lot of social media sites such as our YouTube channel, which has recorded webinars such as these, which you can feel free to refer to, great for learning purposes as well. Our email for our Philadelphia office is info-us info-us at dlubal.com. And the phone number is 267-702-2815. If you guys have any questions or would like to discuss anything that you saw today or anything else, feel free to email or to call. We will have plenty more upcoming webinars. You can register at our website, dlubal.com. At the top, you have the options support and learning and then webinars. As you guys know, I also like to send out reminder emails about these webinars, so certainly look for those in the future. Now, many of you are wanting Pdh credit for today. That's great. I'll be happy to issue you a certificate. I just ask that you request the Pdh certificate through email at info-us at Dlubal, that's DLUBAL.com. Again, info-us at Dlubal.com. Just send me your name, possibly if there were other attendees in the room, and I can issue those certificates to you. And with that said, that concludes our webinar today. So of course, thank you for coming, and I do hope to see you at the next webinar.